In June 2026, a team of astronomers pointed the Euclid Space Telescope at an ancient star cluster looking for one thing and found something else entirely: a gap. A patch of stars that should have been there, sitting right in the data, simply missing. This is a real peer-reviewed discovery, published just weeks ago, and nobody was even looking for it when they found it. The cluster in question is called NGC 6397, one of the closest globular clusters to Earth, sitting roughly 8,000 light-years away in the southern constellation Ara. Globular clusters are dense, roughly spherical collections of hundreds of thousands of stars held together by their own gravity, and they rank among the oldest structures anywhere in our galaxy. NGC 6397 itself is estimated to be about 13.4 billion years old, meaning its stars formed when the universe itself was still in its infancy. It's also what astronomers call a core collapsed cluster, one of at least 20 known globular clusters in the Milky Way, whose central region has contracted over billions of years into an extraordinarily dense, tightly packed core of stars. NGC 6397 has actually been catalogued for a remarkably long time by astronomical standards. It was first identified by the French astronomer Nicolas Louis de Lacaille back in 1752, more than 2.5 centuries before Euclid ever captured a single pixel of data on it, and it's sometimes still referred to by its alternate designation, Caldwell 86. But history matters here in a small but meaningful way. Astronomers have been staring at this exact patch of sky for hundreds of years, through generations of steadily improving telescopes, and this particular feature, hiding inside one of the best studied star clusters in the sky, still managed to stay completely undetected until 2026. That's a genuine testament to just how subtle this signal actually is, and how much observational precision it took to finally pull it out of the data. A team from the Space Telescope Science Institute in Baltimore, led by researcher Massimo Grigio, set out to study this cluster for a fairly specific purpose, measuring the internal motions of its stars using combined data from Euclid and the Hubble Space Telescope. That's a genuinely difficult technical challenge in its own right. NGC 6397's stars are packed so tightly together that separating one star's light from its neighbors requires extraordinarily precise photometry and astrometry, techniques for measuring exactly how bright a star is and exactly where it sits, refined over more than 2 decades of Hubble observations of crowded stellar fields. The team wasn't hunting for anything unusual. They were doing careful, methodical work mapping how stars move within one of the most crowded stellar environments in our galactic neighborhood. Studying stellar motion inside a core collapsed cluster like this one isn't just a technical exercise either. Astronomers care about these internal dynamics because they can reveal evidence of hidden mass concentrated at a cluster's center, potentially including intermediate mass black holes, a genuinely elusive category of black hole that sits between the stellar mass black holes formed from individual collapsed stars and the supermassive black holes found at the centers of entire galaxies, confirming their existence has proven remarkably difficult, and precisely tracking how stars move within a dense cluster's core is one of the more promising ways to search for their gravitational fingerprint. That was the actual scientific goal driving this observation campaign, not stellar brightness gaps at all. While sorting the cluster's stars by brightness and color, a standard technique astronomers use to study stellar populations, something jumped out that had no business being there. A narrow, unmistakable gap appeared in the data, a band where a specific population of low-mass red dwarf stars should have shown up in significant numbers, based on everything astronomers understand about how stars of different masses are distributed within a cluster this size and age. Instead, that band was almost empty. Co-author Andrea Bellini put it plainly afterward, saying the discovery was serendipitous, that the team wasn't looking for the gap at all, but found it anyway sitting in plain sight once they organized the data the right way. If watching scientists stumble onto something genuinely unexpected, while doing completely unrelated work, is exactly the kind of real discovery story you come here for, go ahead and subscribe, because that's precisely the kind of science this channel exists to track down. Here's why this particular gap mattered enough to become its own published paper rather than a footnote. Astronomers had actually seen something like this once before, back in 2018, in an entirely different context. Using data from the European Space Agency's Gaia mission, which precisely maps the position and brightness of stars scattered throughout our galactic neighborhood, a researcher named Ting Zhao and colleagues identified a similar narrow gap among nearby field stars, individual red dwarfs scattered through the Milky Way rather than packed into a dense cluster. That feature became known as the Zhao gap, and it had never been confirmed inside a globular cluster until this new Euclid and Hubble data came along. Finding the same signature in a completely different, far more crowded environment wasn't just a repeat observation. It was confirmation that whatever process causes this gap is a fundamental feature of how certain stars evolve. not some quirk specific to the loosely scattered stars Gaia originally studied. So, what's actually causing a specific population of stars to essentially vanish from a cluster's stellar census? The leading explanation involves something happening deep inside the stars themselves, invisible from the outside, except for its effect on how bright they appear. Stars below a certain mass transport their internal heat and energy differently than larger stars like our Sun do. In a star like the Sun, energy moves outward through a combination of radiation in the deep interior and convection, a churning, boiling motion similar to water heating in a pot closer to the surface. In the smallest, coolest red dwarfs, convection takes over the entire star from core to surface with no radiative zone left at all. Somewhere in between those two extremes sits a narrow range of stellar mass where a star transitions from being partially convective to becoming fully convective throughout. And researchers believe that transition happens quickly enough and changes a star's internal structure and luminosity output significantly enough that very few stars actually get caught sitting at that specific brightness for long. Stars pass through that stage rapidly on their way to a more stable configuration rather than lingering there the way they do at most other points along their evolutionary path. And that rapid transit is exactly what leaves behind an observable gap when you count up how many stars sit at each brightness level. To picture why a rapid internal transition would leave a visible gap in the data, it helps to think about traffic on a highway rather than stars in a cluster. If cars mostly travel at a steady, consistent speed, except for one short stretch of road where everyone briefly accelerates through a downhill section, a photograph taken from above at any random moment would show plenty of cars everywhere except that one brief stretch, simply because vehicles pass through it too quickly to be caught there often. Stars work in a broadly similar way over cosmic timescales, because they spend a comparatively short span of their multi-billion-year lives passing through this specific structural transition, and a comparatively long span of time on either side of it in more stable configurations, a snapshot of the cluster's entire stellar population, exactly what Euclid and Hubble captured, naturally shows fewer stars sitting at that particular brightness than at any other point along the sequence. Red dwarfs are, by a wide margin, the single most common type of star in the entire Milky Way, which is part of why a gap affecting them specifically was significant enough to study closely once researchers noticed it. There's a genuinely elegant scientific payoff hiding inside this otherwise obscure stellar physics detail, because this convective transition happens at a very specific, predictable stellar mass, and because physics tells researchers almost exactly how intrinsically bright a star should be at that precise transition point, the gap functions almost like a built-in ruler. Russell Ryan, another of the paper's authors, explained that because scientists can pin down the true brightness where this gap occurs with very high precision and know exactly what stellar mass produces it, they can compare that known brightness against how dim the gap actually appears from Earth to calculate the cluster's distance with considerably more precision than many existing methods allow. In other words, a strange missing patch of stars turned out to double as a remarkably useful cosmic measuring tool, one astronomers hadn't previously had reliable access to for clusters this old and this far away. It's worth understanding why nobody had spotted this inside a globular cluster before, given that the underlying stellar physics driving it would apply to red dwarfs anywhere in the galaxy. The answer comes down to raw observational difficulty. Globular clusters pack an enormous number of stars into a comparatively tiny patch of sky, and resolving individual faint red dwarfs cleanly apart from their densely packed neighbors requires both extremely sharp imaging and extremely careful photometric analysis, precisely because so many stars sit so close together from our vantage point. Euclid brought something crucial to this specific problem, a remarkably wide field of view combined with sharp, stable imaging, allowing researchers to survey a broad swath of the cluster's stellar population in a single coherent dataset. Layering that wide view on top of Hubble's decades of refined, crowded field photometry techniques, developed specifically to pull individual stars apart from dense stellar backgrounds, finally gave the team the combined resolution and coverage needed to catch a feature this subtle. Gaia, the mission that first spotted the same kind of gap back in 2018, actually had a much easier task in one specific respect. The stars it studied were scattered individually across our galactic neighborhood, close enough to Earth and spread far enough apart that measuring each one's brightness precisely didn't require untangling it from a dense crowd of neighboring stars. NGC 6397 presented the opposite problem entirely. Hundreds of thousands of stars crammed into a region of sky small enough that many of them visually overlap from Earth's perspective, at a distance roughly 1,000 times farther away than most of the field stars Gaia originally studied. Finding the same physical signature under conditions this much more challenging is exactly what gives researchers confidence that the underlying mechanism is a genuine universal feature of red dwarf physics, rather than some artifact specific to how Gaia happened to observe its own sample of nearby stars. This discovery also fits into a broader, genuinely interesting pattern in how Euclid has been operating since it began science observations. Euclid's primary mission has nothing to do with individual star clusters at all. It was built specifically to map the large-scale structure of the universe, hunting for evidence of dark matter and dark energy by charting the positions and shapes of literally billions of galaxies across roughly a third of the entire sky over its planned 6-year survey. That means discoveries like the NGC to 6397 gap tend to emerge as genuine side effects of an instrument built for an entirely different purpose, byproducts of Euclid's raw observational power getting pointed at all sorts of targets along the way, sometimes turning up findings nobody on the original mission planning team specifically anticipated. That pattern has shown up elsewhere in Euclid's recent work too. In June 2026, the same month this star cluster paper came out, the mission also released its largest and most detailed image of the Milky Way's own galactic center ever produced, a mosaic built from tens of millions of individual stars, captured across roughly 26 hours of observing time. That image wasn't just a pretty picture either. It was specifically designed to give researchers a head start mapping a region of sky that NASA's upcoming Nancy Grace Roman Space Telescope will study in far greater depth once it launches, allowing scientists to identify foreground stars likely to produce microlensing events, a phenomenon where a foreground star briefly magnifies the light of something behind it, sometimes revealing distant planets in the process, well before Roman even reaches orbit. Euclid has also recently launched a public citizen science project called Space Warps, inviting ordinary volunteers to help comb through its images. For gravitational lenses, cases where a massive foreground galaxy bends and distorts the light of something even farther away, another tool researchers use to map where the universe's invisible dark matter is actually concentrated. Taken together, that context helps explain why a mission designed to study the largest, most abstract structures in the universe ended up producing one of the more delightfully specific stellar physics discoveries of the year, almost by accident. Euclid's fundamental design, wide field of view, sharp and stable imaging, and an enormous, ever-growing archive of data covering huge patches of sky makes it exceptionally good at turning up unexpected patterns, whether researchers are looking for them or not. It's worth being clear about what this discovery does and doesn't represent, because a headline about a mysterious gap in space understandably invites some imagination. This isn't a case of missing matter, an unexplained void, or evidence of anything exotic happening at the level of dark matter or fundamental physics. It's a genuinely fascinating but entirely conventional astrophysical signature, a predictable consequence of ordinary stellar structure playing out inside stars too small and dim to study this precisely until instruments like Euclid and Hubble could be combined this effectively. The mystery here was never about what the gap is. Researchers identified the likely physical cause fairly quickly once they found it. The genuine achievement was detecting a signature this subtle at all, buried inside one of the densest, most crowded stellar environments in the galaxy, entirely by accident, while looking for something completely different. Researchers involved in the study have already said they plan to keep searching for this same convective transition gap in other globular clusters, using continued Euclid observations, and eventually using NASA's Roman Space Telescope once it begins its own survey work, finding the same feature consistently across multiple clusters with different ages, compositions, and distances would let astronomers refine this distance measuring technique considerably, and would help confirm that the physical mechanism behind it works the same way across a wide range of stellar environments, rather than being some quirk specific to this one particular cluster. Roman, once it launches later this year, is expected to survey vastly larger stretches of sky than either Euclid or Hubble can manage individually, giving researchers their first realistic shot at testing whether this gap is truly a universal feature of red dwarf stars everywhere, or something that varies meaningfully from cluster to cluster. There's something worth appreciating about how this entire discovery came together, start to finish. A telescope, built to study the invisible scaffolding of the universe, ended up, almost as a side note, revealing something intimate about the internal machinery of ordinary stars. Stars so faint and so tightly packed together that nobody had managed to resolve this particular signature inside a cluster before. Nobody set out looking for it. The team was doing careful, unglamorous work, mapping stellar motion, and the discovery simply sat there in the data, waiting for someone to sort the numbers the right way and notice that something expected wasn't showing up. This is also a useful reminder about how much of modern astronomy actually works, quietly, methodically, and often without any dramatic announcement attached. Most headline-grabbing space stories involve something enormous, a black hole, a planet-sized impact, a signal from across the galaxy. This discovery involved none of that. It involved a small, patient team carefully counting stars by brightness in an old, well-studied cluster, and noticing that the numbers didn't quite add up the way 3 centuries of prior observation had led everyone to expect. That kind of careful, unglamorous bookkeeping is where a genuinely surprising amount of real scientific progress actually happens, even when it never makes for a dramatic headline on its own. It's also worth remembering that this discovery is very much a beginning rather than an ending. A single confirmed detection of this gap inside one cluster raises an obvious next question: whether the same feature shows up consistently across other globular clusters scattered throughout the galaxy, each with its own age, distance, and chemical makeup. If it does, astronomers will have a genuinely new, remarkably precise tool for measuring distances across some of the oldest structures in the Milky Way. If it doesn't show up consistently, that inconsistency itself would teach researchers something valuable about what other factors might influence exactly when and how this stellar transition unfolds. If deep dives into real astronomical discoveries, the kind that turn out to be genuinely surprising without needing anything, invented or exaggerated, are what you come here for, make sure you're subscribed, because there's a lot more of this kind of story coming out of Euclid's ongoing survey. And if a missing patch of stars, turning into a new way to measure the universe, surprised you as much as it surprised the researchers who found it, let me know in the comments, and I'll see you in the next one.